So here for example 4, they throw in part 1 of the fundamental theorem of calculus. And the AP test loves to do that too. They like to just sort of throw it in there randomly. Actually, another reason why it's thrown in here is because we have a product of two functions, which we know we cannot split over an integral. So to find the antiderivative of this, we're going to kind of cheat and use fundamental theorem of calculus part 1. Now, if you recall, fundamental theorem of calculus part 1 basically said, oh, the antiderivative, no problem. That's just the function of the area under the curve of little f from, actually I should call this a, from some constant a to x. Oh yeah, and these were f of t and dt, so not to be confused with that x. So again, these were just a dummy variable just to tell you the name of the function. This was the actual real variable, the thing that would be changing. And if you remember what the picture looked like, you have like your function, here's f of x, and you have a right here, and then this upper limit is allowed to vary. I can slide it. I can either have it really close to a, or I could slide it way over here if I wanted. And then wherever I chose to slide it is going to affect how much area is under the curve. So if I had put the x right here, I'd only have a teeny sliver of area. But since I slid the x all the way over here, I have a nice big chunk of area. So in other words, this area function is going to vary depending on where I put the upper limit of integration. So that's what part 1 says. So for a, I can just say, oh, easy, no big deal. You want to find the antiderivative? Oh, that's just the area under this curve. And we can go ahead and use 0 for our bottom limit. From 0 to x of, but now we can't use x in the function anymore. Now that I have this as a variable, I'll just call these t. T squared cosine t dt. Oh, and plus a constant. Done. So it's kind of our way of cheating. We weren't able to find an antiderivative of this because it's a product, and I can't split the integral over products. So I just say, oh, the antiderivative, that's just the area under the curve from 0 to x. And then, of course, plus a constant, because then I could take the derivative of this. If I took the derivative of this, I'd have x squared cosine x. And the derivative of the constant is just 0. So when in doubt and you don't know what to use for a, 0 is the best go-to. Okay, now for b. It wants us to find a specific antiderivative whose graph passes through the point 0, 1. So in other words, what that means is solve for c. So I'm going to plug in 1 for big F and 0 for x. So I'm going to get 1 is equal to the integral from 0 to 0, because this is where you plug in the variables, the upper limit. T squared cosine t dt plus constant. Well, we learned back in, I forget what section it was, but we learned what was called the zero integral or something like that, where if you have the same upper limit that you do as a lower limit, that means there's no change in x, there's no area. So that's equal to 0. So you have 1 equals 0 plus c. So c is 1. So the answer for b is you would say, okay, f of x is equal to the area under the curve from 0 to x plus 1. So it's our little way of cheating when we are unable to find an antiderivative. Now, by the way, there is a way to find the antiderivative for that, but you won't learn that actually in this class because we use what's called integration by parts, which is not on the AB exam. If you are interested in learning it, though, I can teach it to you and let me know. I could do some sort of extra credit. So instead of finding the actual antiderivative, we're going to cheat and use part 1 of the fundamental theorem of calculus, using 0 as our lower limit of integration. Okay, moving on to the last example. So this one likes to kick it up a notch. Of course, the last example always does. And it wants us to solve not just, we have to find basically 2 antiderivatives. I have to back up all the way from the second derivative all the way to y. So I got to do two antiderivatives. So let's begin by separating the variables. So I got a second derivative of y, second derivative of x. So I begin by separating the variables. I'm going to go ahead and integrate both sides. Oh wait, actually I don't really need the one here. So the antiderivative of the second derivative of y would just be the first derivative of y. The little 2 goes away. And then here I'd have 2x, 2x, and then minus 6x squared over 2. And then the dx squared becomes a dx1. So second derivative becomes first derivative. Okay, so now I notice that, oh, I forgot plus c. Hold on. Don't want to forget plus c. Because I need to solve for c basically before I go on. So I notice right here they told me that y prime of 0 is 4. Well, we need to remember that y prime is the same as dy dx. So I'm going to just momentarily put the dx back over here so I have y prime basically. So I divide the dx back over and I get 2x minus 3x squared plus a constant. But I know that when x is 0, dy dx is 4. So I'll plug 4 for dy dx and 0 for x. And I get that c is 4. So now I know that dy dx is equal to 2x minus 3x squared plus 4. So I'm going to move the dx over to the other side because I need to basically separate my variables again. So I get dy is equal to 2x minus 3x squared plus 4 dx. So I separated my variables up here, but they were double derivatives. So when I took the antiderivatives of them, I got single derivatives. Then in order to solve for the constant for the first derivative, I put the dx back over here because that's the same as y prime. So that basically is equal to 4 when x is equal to 0. Solve for c. So now I solve for the first derivative. So now I'm basically taking this over from like the beginning of the other problems we solved. I'm going from the first derivative back to the original. So again, I begin by separating the variables, and then I'm going to integrate both sides. And then here's where I notice I have the 1. Now this is a single derivative, so when I take the antiderivative of it, it goes away, and I'm just left with 1y. Here I'd be left with x squared. Here I'd be left with x cubed. Here I'd be left with 4x. And then, of course, always have to add a constant. And the dx goes away because this was just a single derivative. So the antiderivative of that cancels out, and it goes away. And the last thing I need to do is solve for c using the other initial condition I was given. I was told that y, which is this right here, is equal to 1 when x is 0. So I have the point 0, 1. So I can plug 0 in for x and 1 in for y. So I get 1 is equal to 0 squared minus 0 cubed plus 4 times 0 plus c. And I get that c is 1. So I'm finally able to answer this question because this question again was asking me to find y. I'm now finally able to do that. I know that y is equal to x squared minus x cubed plus 4x plus 1. So if you're not sure, you could go ahead and find the first derivative of this to check and see if you get this. So first derivative would be 2x minus 3x squared plus 4. And that's what I have here. Then I could find the derivative of this, which is just 2 minus 6x, which was the original. And I also notice that if I plug in 0 into this derivative, I get 4. So it satisfies that condition. If I plug 0 into this function, I get 1. So both of these conditions are satisfied, and this is the double derivative of this. So these problems are great in the sense that you can always check and make sure you did them right. And that's finally all for 6.1. And I'll see you in class.